Alright, so let's have a look at question 2 in January 2012, Unit 4. So this is going to be about capacitors. So first of all, as often questions do in Unit 4, we're starting with a definition question. So the definition of a capacitance. So capacitance is the charge stored. So that's what a capacitor does, it stores charge. So it's the charge stored per unit of potential difference. It would help if I could spell potential. There's no letter in there. Potential difference. Okay, so that's the definition. So in terms of that, so capacitance is essentially the charge stored per unit potential difference. So essentially you're describing this equation. Key things people miss out. People often forget to talk about the fact it's charge stored and forget to say it's the unit of potential difference. Okie dokes. So we've got a circuit. So we've got a charging EMF source, a resistance, a capacitor, and a switch. Switch is closed. The graph shows charge stored by the capacitor varies with T. The capacitor is fully charged. Charge stored is 13.2 microcoulombs. The electromotive force of the battery is 6.0 volts. Determine the capacitance of the capacitor. Okay, so towards the equation I was just talking about. So Q over V. So it would be 13.2 micro is 10 to the minus 6 divided by the potential difference, which is 6.0, and if we do that we'll end up with a value of 2.2 times 10 to the minus 6 farads. Okie dokes. Okay, so that's that one. So let's on to the next question. So the time constant of the circuit is the time for the charge to increase from 0 to 63% of its final value. Use the graph to find the time constant in milliseconds. So let's flick and look at the graph. Okay, so if we read from the graph, essentially if you look at the graph, you can read off the value. So we're looking for, let's find out what the value is we're looking for. So we're looking for 0.63 times by 13.2, which is the final value. So we're looking for the point where there's 8.3 microfarads. So if you look at your graph and you read off, you should get approximately 15 milliseconds for the time constant. So essentially you're looking for this value and reading off a time for that value, and you'll have a small variation, usually plus or minus 1 milliseconds to get that right. So from that we want to calculate the resistance. So we should know the time constant is RC. So R would be T over C, which is 15 divided by the capacitance value we got earlier, which gives you an answer of 6.8 times 10 to the 3 ohms there. Okay, so what physical property is represented by the gradient of the graph? So if on your y you have Q and on your x you have T, so the gradient of a graph is going to be the charge per unit time, which is also called the current. Okay, so the maximum value of current in the circuit during the charging process. So the maximum current will be when the whole potential difference is across the resistor, so it's going to be 6.0 divided by the unrounded version of this, which is like 6.820 blah 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 blah, and we put that in and we do the calculation. You should get 0.8 milliamps. So that would be the maximum current, and obviously this value at the top line would decrease over time, so it would be maximum initially and the current would decrease over time, which leads on to the next question. So we're showing how the current varies with time as the capacitor is charged. So whether it's charging or discharging, a graph would always be a exponential decay for the current. So it looks something like that, and then on this axis this would be 0.88 milliamps at the start, and it should be pretty close to 0 by 60 milliseconds. So look something like that. Okay, so this concludes the series of videos on the sections of this exam that relate to the content covered with me.